before watching this video. If you read through the relevant chapter in HRK already, or maybe Purcell's, feel free to skip to the second part of this video series. We're going to start with gravitation. Nothing too interesting here. Just a quick note, if you're going to find the gravitational force between two masses that are not perfectly spherical or that do not have spherical symmetry, and furthermore are not infinitesimal such that you can consider them to have spherical symmetry, what you're really going to have to do is that you're going to have to integrate over every single particle in each mass and find the contributions to the gravitational force from each of those objects. And the force is of course directed along the line connecting the two masses. Coulomb's law is very similar to Newton's law of gravitation. We have G is replaced by 1/4 pi times the electric permittivity of free space. And note that there's a reason that we have this huge constant instead of a simpler constant as in gravitation's case. And the masses are replaced with charges. Lastly, this force can be repulsive as well as attractive. And the details of that sort of interaction is in the text. So we'll move on to fields, and I'm not really going to go too much over fields here, but we're going to talk about field lines because field lines are very integral to our understanding of Gauss law. The idea of field lines here is that, let's say we have a charge Q and it's positive, or it can be negative. Let's just talk about a random distribution of charges. Let's say negative Q, whatever, right? And we can even make this more general by not even considering the charges and just considering an electric field at a bunch of points. We're going to draw the field lines as follows. We're going to place the field lines. We're going to place a random charge in space, let's say charge Q1. And we're going to observe its motion. Let's say it moved like this for some reason. Then we draw that as a field line. Then what we're really supposed to do here is we're supposed to iterate over all points in space and draw every single path that every single point or slash charge takes. And those are the field lines per se. There are some complications, and this isn't a technically correct definition, but it should help you enough to accurately answer the questions that will have to be answered. And note that the field line is really representative of the field at a point, as for example the field line here is like, we can say it's going in this direction, and the field will actually be in the tangent direction. So just where the field line is going at that point. So field lines are important because when we deal with flux, we're going to be dealing with integrals that we don't want to calculate. And so what we can really do is think about field lines as somewhat related to flux. And honestly, this picture looks a lot simpler to me than this picture, right? So let's deal with this. That's what field lines are. You can Google about those more if you want to. It's not too difficult to find all the information you need to know about field lines. Right before we get into Gauss law, I'm just going to take a second to go over an analogy to power of a point. Electric fields and gravitational fields are intrinsic properties, or are at the very least properties of only the body that makes them. So the power of a point in space, due to some circle, is, well, we can say that it is a property of the circle and not so much a property of the arbitrary point that we pick. So this point has a power P1, this point has a power P2, and these are really just properties of the circle, just as the electric fields are properties of the charge that creates them, and gravitational fields are properties of the masses that create them. Alright, so now we're going to go on to Gauss law, and this is going to be the meat of our presentation here. So I'm going to give you guys like 10 seconds to just look over this. We'll be spending a bit of time just explaining what the integral means, so if you already know what that means, you can like try to skip ahead. So we're going to be taking a mathematical perspective on Gauss law, which means we will not be considering the effects of induction and that sort of thing in changing our views on Gauss Law. But it is important to note that we will be talking about exactly what a closed surface is, and in fact I will construct a closed surface right now, and that sort of thing. So a closed surface is pretty much exactly what you think it is. It's a surface such that any point within the surface and any point outside the surface can only be connected by a line that crosses through the surface. So it means pretty much what you think it means. And now we talk about Gauss Law. So I'm gonna state Gauss Law here, and then we'll just go over like what all the terms mean. All right. So first, this is the easiest of them all. This is just the permittivity of free space. I'm not even gonna put an arrow there. It's just a constant. And this next part is the surface integral, and as that might not be immediately obvious what surface integral means, we're going to talk about it much like people have talked about calculus with Riemann sums. So what's going on here? What we're really doing is we're taking, let's say we're taking a plane, and we're taking a plane to subtend a bunch of points. So that'll be our first plane. This will be our second plane. Let's say this is the third plane. And so for each of these planes, we're just going to keep taking more and more planes until we cover the entire surface. And we'll make the planes such that they're tangent to the surface at some point. And these planes will all have areas. Let's say this has area A1, this has area A2, A3, A4, right? I hope you guys can see that. And so now what we're really going to want to do is we're going to want to observe the electric fields at each of these points. So let's say that the field looks something like this. These are just some field lines that I'm drawing. They're not even complete field lines. So what we're really going to want to do now is, right before we get into the calculation, we're going to want to construct the normal vector at each of these planes. And note that ideally they will cover the entire surface. So the normal vector here might look like this. Here might look, well, it would be coming out of the page, but I'll try my best to approximate that. Here it would look like this. Here it might look like this. Right? And so now the final idea is we're going to go over every single plane that we have here. We're going to take the field at that plane, right? And we can take the average field over points in that plane. So we could say like EAV. And we're going to multiply it, or we're not going to multiply, we're going to dot it with an area vector. What is the meaning of this area vector? Well, this area vector is just going to be the unit normal. So let's call this n, right? All of these normal vectors n's. N3 and 4, the unit normal, so N3 times, or let me say NK to keep this just a bit more general. NK times AK. And just one more thing, this is not actually correct. I will make this a bit more obvious. So I'll say NK over NK. And so hopefully this vector notation is obvious what's going on here. And this is the average E average in this field K. And so we're just going to be summing up all of these dot products. So what is this term? What is this term? This term is actually what we call the area vector, which is a vector which has the magnitude of the area of the thing it's subtending as its magnitude. And it has as its direction the direction of the normal vector that is perpendicular to that plane and that points outward from the surface. So as you can see here, these n vectors, we say n1, n2, n3, as you can see here, this would be n1, n2, those are in the same direction as this area vector. And let me just say equals A, right? So that's just the definition of the area vector. And so now we're just going to sum over all our planes, the average field on that plane, dotted with this area vector. Note that this area vector, I'm just going to repeat it once more, has magnitude that corresponds to the area of the plane and direction that corresponds to the normal vector, or I should say the direction that corresponds to the normal vector at that plane. And so now the formulation to an integral should be pretty obvious. What we do is we just make these planes extremely small, and so this summation turns into an integral. We're going to call this a closed surface. So now E average at some point is just going to be the electric field at that point because you made it extremely small, the plane. And this surface area thing is just going to be dot dA. And it's going to be dot dA because as we make this plane smaller and smaller, let me draw smaller and smaller planes. Maybe it looks like this. And then at some point, it's just a point, right? That's not a point, but it's all right. So as you make this smaller and smaller, we're really considering infinitesimal areas. And since the normal vector has magnitude, which is equal to the area of the plane that it corresponds to, and since its magnitude is getting smaller and smaller, the normal vector, or the area vector, gets smaller and smaller as well. And so it becomes dA. And so that's all this integral really means. We're just going to add up a bunch of dot products, essentially. In the very end, I hope it's now clear, but the Q that we're talking about, I'm going to put it in blue, is actually a charge enclosed by the surface. So let's say within this closed surface, so you can't really see inside, but if you took like a close-up view of this surface without all the random lines hanging around, there might be a charge Q inside this. And this charge Q would actually be equal to this integral we have times the permittivity of free space. So just a few things to point out. No matter where this charge is, if we move this charge here, move this charge here, wherever we move it, we're saying that this integral does not change, which is somewhat interesting. It's been defined in such a way that it doesn't change. And furthermore, well, we won't talk about this, but this field analogy is somewhat interesting in that even if we have a charge outside, say charge Q2 outside the field, the charge, first of all, does not change the surface integral. And sometimes it will change the field, but the value of the surface integral will remain unchanged. So there's a lot of things to look into there, and you can read about most of them in HRK in the relevant chapter. But the main idea is that this integral times the electric permittivity of free space is equal to the charge enclosed within. Now, it's important to note that if you have a charge outside, and we're not talking about the contributions of this charge to an electric field. We're just talking about the surface integral of, like, this surface integral, right? This does not change what this Q ends up equaling. This Q is just the Q enclosed by the surface. And if we add a charge inside the surface, let's say Q2, then it will change this. And so I just want to make sure that it's clear that this is the net charge within the surface. So equals sum of QMs, okay? This is just net charge enclosed by the surface. I hope I went over this in sufficient depth. You guys can feel free to ask questions in Discord if you have any questions about this. We're actually not done with Gauss Law, even though I spent an inordinate amount of time going over its basics. There's one last thing, which we'll actually use a lot, and that's that this surface integral of E dot dA, which we've been talking about so much, can be thought of as proportional, or we should say over a closed surface, not even over a closed surface, over any surface, can be thought of as being proportional to the number of field lines crossing through the surface. And so we've already talked about field lines before. Let's talk about this statement for a bit. So first of all, the integral, or the surface integral of E dot dA is defined for things that are not closed surfaces, right? We can always still take dot products. It's interesting to note that if we have a surface that isn't defined, like a line or something, we don't really have a good definition for the outward normal. And so we really take the flux to equal, in this case, the number of field lines crossing through this line for this case. This might seem like a weird analogy, so I'll make this a square just so it makes a bit more sense. It'll be the number of field lines that crosses through the square. Now, a few notes. First of all, obviously we can draw an infinite number of field lines to cross through the square, which is why we have this proportionality symbol, right? The idea here is that if we now have a square that only subtends like half of these field lines, then even though like the number of field lines crossing through the square is also infinite, it's sort of like half of this infinity. So the flux through here, the integral through here, let's say this is integral 2, this is the integral 1, then we have that integral 1 equals 2 times integral 2, right? So the ratios between the number of field lines in various cases is really what's interesting to us. Secondly, it's important to remember that when we talk about field lines crossing through the surface, we have to be a bit careful about what we mean by crossing through. So if we have, in some case, a closed surface, then we really have to consider a field line that crosses through the opening and through the closing of the surface as canceling one another out. And here's why. When you're taking this integral E dot dA over a bunch of lines that cross through both times, here the surface normal is going to be this way, and here the surface normal is going to be this way. So here the dot product is going to be negative, here the dot product is going to be positive. And if you draw your field lines right, and by right I mean you don't use the fluid analogy that I've talked about already, which is sufficient to solve problems but not sufficient for a detailed analysis, these pluses and minuses have equal magnitude for every single field line, meaning if a field line crosses through the surface twice in like its journey, its contribution to this flux is 0. It's negative x here and x here. Alright. So of course, this should also help give some insight on what field lines have to do with the enclosed charge, because if we have a charge enclosed within the surface, Q, all of a sudden, it's not entering and exiting, it's only exiting. And so we only have, in this case, a positive contribution to the electric field at this point, as the outward normal here is parallel to the field line, and the outward normal here is parallel to the field line. We never have like a backwards case as we did when the field line was both entering and exiting. And more generally, if the field line is entering, it's going to contribute a negative thing, and if it's exiting, it's going to contribute a positive amount to the surface integral. And since things within the surface can only exit if they can only contribute positive amounts, the specific field lines can only contribute positive amounts to this dot product summation. Hopefully that wasn't too much of a mouthful. This is actually quite important, this analogy of using field lines to simplify our calculations of flux. This is probably the most principal problem in all of Gauss Law, which is finding the electric field associated with an infinite plane some perpendicular distance d away from the plane. So let's do that. We have a plane. We have plane, it has charge. This is quite unfortunate. Let's do yellow charge. Okay. It actually has a uniformly distributed charge, and we're gonna assume uniform distribution. But we can actually show that while uniform distribution makes our formula extremely precise, slightly non-uniform distributions, as occur in real life, are pretty much exclusively what we use this sort of analysis for. So we have a uniformly distributed charge across this surface, right? And it's going to be an infinitely large plane. So this is going to extend extremely long in every direction. And so this charge is also going to be infinite, or it can also be non-infinite, but the analysis there is extremely similar, and there's honestly no point in going over that. And so since the charge is infinite, the quantity that's relevant in this case is really going to be charge per unit area, and we're going to denote this omega. So we have this plane extending forever with charge, which is yellow. The idea is we try to find the field at a distance d from the plane. And the crucial step is actually very similar to geometric construction. We're just going to construct a cylinder of radius r that passes through this plane, and its faces are parallel to the faces of this plane. Right? So the cylinder has radius r, it's a distance d from the plane, and it extends on both sides for a distance d. Now, what we're really going to do is we're going to analyze Gauss Law for the cylinder. So the first thing we need to consider are the field lines of this infinitely long plane and the electric field at various points. So the first thing to notice is that the electric field at various points is going to be directed directly up, or we can say directly up at every single point that's anywhere. If it's below the plane, it's going to be directed directly down. And so the idea here is that if there's a point in space here, right, then the field vector can only be directed directly up, because if it's not, then there's a violation of symmetry. If it's, let's say this is the radial vector from the plane to the point, it's perpendicular. You can draw like a little right angle. And let's say the field is this way. Well, this violates symmetry. Why? Because we rotate our entire diagram, let's say like 15 degrees. We rotate 15 degrees. And now all of a sudden, the vector is this way. But we just analyzed this and we said that the vector was this way. And so that's an obvious contradiction. The only way we can rotate and not get a contradiction is if the field line is directly up. The field line could also be directly down and not violate symmetry, but at this point you should realize that since field lines are defined the way they are, it should be looking like it's directly up above the plane and directly down below the plane. Now, we know that the field line everywhere is directly up. So now we're looking at a large cylinder, and the cylinder has two types of faces. It has curved face and it has like a circular face. It has two circular faces, in fact. And this curved face, all the field vectors are going to be directly up. It's still going to be directly up. And so let's look at like a random point for this field. It's going to be directly up for the field, and for the cylinder, the normal vector is going to be it's going to be perpendicular to this directly up field line. And so the dot product, pairwise dot products that we're going to be taking over any point on this curved portion of this cylinder, they're all going to be zero. Recall that dot products are zero when vectors concerned are perpendicular. So we don't even have to consider these things when we're talking about the surface integral of E dot dA. And I'm going to write this down. integral of E dot dA is what we're trying to find right now. And we're saying that if we're finding this over the surface, this is equivalent to the surface integral of E dot dA over two circles on cylinder equals cylinder. Now what do we know about the field vectors on the cylinder? Well, we know they must all have the same magnitude everywhere on the circle. And why do they have to have the same magnitude? We again look at symmetry. If, let's say, this field vector was bigger than this field vector, we just move our eyes to the right or to the left, and there's a contradiction. I hope that's apparent. We can't have any sort of variation in the field vectors, or else symmetry is violated. And furthermore, the magnitudes of the field vectors here downwards have to be the same as the magnitudes of field vectors here upwards. Again, by symmetry, we rotate the entire plane upside down, and we have to have the same image. So we have the same field vector at every single point. And those are actually outward normals, but I'll draw the field vectors now. Same field vectors, which are blue, at every single point on the circle. Here it's the same field vectors except the opposite direction as they were above. And the outward normal can also be considered the same at every single point. And so what is the surface integral really looking at now? It's starting to look like, it's no longer looking like a bunch of varying fields and that sort of thing. It's really just looking like I'm multiplying this vector by an infinitesimal vector in the same direction, dA, and this is going to be what? This is going to be the field. And then I'm going to do that again for this arrow and this subtended area, which is infinitesimal, this subtended area, this subtended area, this subtended area. We're adding up the same thing over and over again. This is sort of like integrating a constant function. See, all these planes have the same field vectors at their points. So at this point, this integral E dot dA on the top is just going to become the field at some point. It's going to be E times A. That's what this integral becomes. But remember, we care about the flux over the closed surface, which means we also need to look at the dot products at the bottom. And these dot products are going to be the same as the dot products on the top. I hope you guys can see why, because here the outward normals, which are red, and the field vectors, which are blue, are parallel. And here too, the outward normals, which are red, and the field vectors are also parallel. Meaning these dot products now are both parallel. They're not going to cancel one another out. And so we actually end up with the total flux, which is this here, over the closed surface, which is a cylinder, which is equal to the total flux over the two circles, is equal to 2 times the field times the area. And what did we say? We said that, well, we said that this, by Gauss Law, we said that EO, surface integral E dot dA equals the Q enclosed. And we just showed that the surface integral is 2EA. And so now we really have equals Q. And so since we define Q over A as omega, we can divide both sides by A. We get omega over 2EO equals E. This, you're actually going to use this so much more than you ever thought you would. Even when it might seem somewhat awkward to think about infinite planes in practical scenarios, you'll see textbooks and the like just considering every single plane that you'll ever find ever as an infinite plane. And that's why this is relevant. We're not going to go over this problem. We might go over it in the next part. And we're going to end off here. The next part will have a few interesting problems to consider, probably the one we skipped here, and definitely a few more interesting problems from later on. And you'll see a lot of problems from HRK in the second part. So if you've already worked through these problems, you should skip to the end where we have an original problem. Thanks for coming.